about amines. I like talking about amine chemistry. And so last class, we finished up to section 22.4. And so today I want to finish through the rest of the chapter. And I'll try not to go overly fast through any of this. Well, now I've already got don't even have my Apple Pencil set up. So let me turn that on. Come on. There we go. All right. So let's go back here and we're done. All right. Now we're on. Okay. So I won't go over anything too quickly, but there are a lot of concepts in this chapter, and I'll be very clear about mechanisms that you need to know. Okay. So going right back to the first amine that you ever would have learned about in General Chemistry 1, what was it, right? It was ammonia, NH3, okay? And then last class, we discussed primary amines. Then we discussed secondary amines, so you know what a secondary amine is. And then, of course, you take that one R group further, and you end up with a tertiary amine. And we said if you added a fourth R group, you can have what's called a quaternary ammonium salt. So take a look here. It says amines are good nucleophiles. That's for sure, right? Amines are very good nucleophiles and readily undergo SN2 substitution with an appropriate alkyl halide. Well, in case you haven't picked up on this at this point in organic chemistry, methyl iodide, which is also known as iodomethane, both names are perfectly acceptable for this compound, is one of the best electrophiles in all of organic chemistry, right? It's very susceptible to an SN2 reaction. And so we have our nucleophilic attack, we have our loss of leaving group, and so we convert ammonia into this quaternary ammonium salt, and then another molecule of ammonia comes along and it does a deprotonation. So we end up forming a primary amine. So the overall, I guess the take-home message here is when you put ammonia in iodomethane, you end up with methylamine, okay, is what you would call this compound. Well, what's interesting is, you guys remember alkyl groups? Could anybody tell me, are alkyl groups like a methyl group or an ethyl group or a propyl group, are these electron withdrawing or electron donating? And it's not a trick question. Would these be electron withdrawing or electron donating? We've seen them many times. We saw them in the chapter on electrophilic aromatic substitution. Exactly. Thanks, Mustafa. These are electron donating groups. Okay, they don't donate a lot of electron density, but they donate some. So like Mustafa said, if this is an electron donating group, that means we have a dipole going in this direction. And so what that means is now the lone pair on here is even more basic than it was in ammonia. So I'm going to put a little line here and say more basic than ammonia. And you could also say more basic / nucleophilic. So this is an even stronger nucleophile. So what does that mean? If you have methyl iodide kicking around, it's going to do it again. Okay, it's going to take that primary amine and it's going to alkylate it again. Okay, then you make a secondary amine. Now you've got two electron donating groups, and you can see where I'm going with this. Is that now it's even more nucleophilic and more basic than it was before. So it does another SN2 until you end up with a tertiary amine, and that is still nucleophilic. So it does another alkylation until we get a quaternary ammonium salt. And we have a name. If you're like, well, this is the reaction that just keeps going. You're absolutely right. It does just keep going. And we have a name for this. We call this exhaustive, like I'm exhausted, right? Like exhaustive alkylation. It's when the nucleophile just keeps reacting and reacting and reacting with every electrophile that comes along. It's exhaustive alkylation. It doesn't stop, okay, until you get to a quaternary ammonium salt. And so the idea is this: if you go back here, if you put 1 mole of ammonia with 1 mole of iodomethane, you end up with a mixture. Okay, you end up with a mixture of products because of exhaustive alkylation. So it's not really the most useful reaction in the world, okay, exhaustive alkylation, but we are going to come back to alkylation a little bit later on. Let's say you want to make a primary amine, right? So if we go back here, okay, what I'm saying is that you go from ammonia to a primary amine here, but it's not a very effective way because it's going to keep reacting over and over and over until you end up with a quaternary ammonium salt. So what if you want to stop here? How would you do that? Well, there's actually several ways you could do that, make a primary amine. So the first one is what we call azide synthesis. Okay, so azide synthesis is a way to make a primary amine. So what we do is we start out with an alkyl halide, right? You guys know the X represents a halogen, so this would be an alkyl halide. And then what we do is we treat that with this compound here. So Na plus N3 minus, this is called sodium azide. So the azide, okay? So that's N3 and it's N3 minus. Now you could try to draw the Lewis structure of that, which looks something like this, okay? It's a very interesting Lewis structure because you have two negative charges, and you have a positive charge in the middle like that. So overall it has a -1 charge and it is a good nucleophile. So once you make the azide, so you would call this an alkyl azide. So this is an azide. Okay, then you end up, you can either reduce that via hydrogenation. That will work to make a primary amine. So again, you have a primary amine, or you could reduce it with lithium aluminum hydride followed by water. Notice that it's not H3O plus, okay? And they're very careful about that because if it was H3O plus, you would end up with the conjugate acid, right? It would protonate the amine because amines are bases. So this is a better way to make a primary amine than rather, attempting to do a monoalkylation, which I told you doesn't work very well. So the mechanism, I will not ask you this mechanism, so I'll even write it here on the slide for you. Will not ask this, but it is nothing straightforward in organic chemistry, but I'd say it's relatively straightforward, right? The first step is a SN2. We have our nucleophilic attack. This part here is the loss of leaving group. And I think the main thing you want to remember in azide, when you reduce it with something like lithium aluminum hydride, which is being shown here, what do you lose? Your leaving group is nitrogen gas, okay? So that just goes up the smokestack. It goes out into the atmosphere. And so this reaction is completely irreversible, right? Once you lose that nitrogen, it's not coming back. So then you do a proton transfer with water in the end. And again, not H3O plus, it's with water. And you end up with your what? With your primary amine. So what's the first way that we learned is azide. So this is called the azide synthesis. So what do? We take our alkyl halide, convert it into an azide, and then we can reduce it with lithium aluminum hydride followed by water, or via hydrogenation. Either one will work, okay? So that's the first one. That's one, okay? We've got a couple more to go. So besides azide synthesis, another way to make a primary amine is to use what's called the Gabriel synthesis. And it says here, not only can you make primary amines, you can also make secondary amines from this fancy molecule. Is this quite a mouthful or what? Phthalimide, right? So, yeah. Anyhow, so from phthalimide or phthalimide. Anyhow, so phthalimide is this compound here. It's probably a good idea to memorize its structure. And you can see that phthalimide, the most acidic nitrogen in the compound, can be removed using potassium hydroxide. It turns out the pK of this proton, I think the pK is around 8, something like that. And of course, that's our acid. Potassium hydroxide is the base. Potassium phthalimide is the conjugate base. And so water is your conjugate acid, which has a pK that's 15.7. So the equilibrium is going to lie to the side of the weaker acid. And so potassium hydroxide is good at deprotonating phthalimide, and we end up with potassium phthalimide. Now, we have a negative charge here on the nitrogen, right? You could draw the resonance structure up here, or you could draw the resonance structure with the negative charge down here, either one. But the bottom line is now this is going to be good at doing an SN2 reaction. Like let's say you had something like propyl iodide like this, the phthalimide ion can come in and it can do an SN2 like that. So here's an SN2. So potassium phthalimide can then be alkylated. And again, we said we could do this with a methyl, a primary, or a secondary alkyl halide. And now all you've done is you've installed the alkyl group onto the phthalimide molecule. If you're like, well, that doesn't look like I'm very close to a primary amine. Good point. So here's what we do. We take this compound here, which you would isolate, and then you've got two possible ways to blow it apart and just pull this part of the molecule out so that you end up with RNH2. Let me show you, okay? One way to do it is with aqueous acid. The problem with this is that it's a two-step procedure, and so my students tend to not be super enamored with this way of doing it because you end up with a quaternary, or you end up with an alkyl ammonium ion, and so you would have to treat this. Where's my black pen? You'd have to take this ion, and then you'd have to treat it with sodium hydroxide in the second step, and then you'd end up with our NH2, right? You'd get the free base like that. So that's with aqueous acid. I mean, again, it's totally fine. You end up with this acid here. This has got a name that might be handy for you. This is called, no, that's not the right spelling. Phthalic, yeah, it was right. Phthalic acid. So phthalic acid is just the common name of this compound, so you can see where phthalimide comes from. But anyhow, so you end up with phthalic acid. You end up with the conjugate acid of the amine, and then you have to deprotonate that using sodium hydroxide. So the first one is actually a two-step procedure. Step 1, H3O plus. Step 2, sodium hydroxide. If you want the old one-step method, all you have to do is treat it with this molecule, and you might remember this from a few chapters ago when we talked about imines and hydrazones, yeah. And this compound is called hydrazine. So hydrazine can be used to go straight from your alkylated phthalimide to give you the primary amine. So here, this way you get the primary amine, and this way is just one step to get the primary amine. Don't worry about drawing the intermediate. I've never made my student, or the other product, I've never made my students draw that product. Anyhow, so there you go. So two possible ways of doing that. And so what this question is asking is, could we use a Gabriel synthesis to make these compounds? So let me show you what the expectations are of the Gabriel synthesis. And this is the way that they do it in the book, and it's the way they do it in ACS. And so all you have to do is this, okay? Take the part that doesn't have the nitrogen attached, okay, and put a circle around that. So in the first one, we'll put a circle around this, and the second one, we'll put a circle around that. And that's where our alkyl iodide is going to come from, or alkyl halide, whatever it is. I just chose iodide arbitrarily in my brain, okay? So you would use this iodide, and then for this one, I'll use a condensed structure because I'm running out of space here, but you use this, and I'll put an iodide. And you say, I don't like that. Okay, fine, let's put a bromine instead, okay? So you would start with that alkyl halide is going to be one of your reagents. So here's the expectations in the textbook, and so I expect the same thing. So you always start with phthalimide. So you have to know the structure of phthalimide. It's pretty quick to draw. Okay, we have, there we go. So they expect you to say, okay, I'm going to start with this compound. In step 1, I'm going to treat it with potassium hydroxide. That would give me the potassium phthalimide. Then I'm going to treat it with the alkyl halide. So in step 2, I'm going to treat it with my alkyl halide, which in this case is this compound. And then we're going to end up with the alkylated phthalimide. So let's draw that out. Get our nitrogen. There we go. So we have CH2, and then we have our 5-membered ring like this. And then to get to the product, all we have to do is treat it with hydrazine. So NH2, NH2, which we call hydrazine, and that is going to give us the product. And of course, you also end up with the side product, which is shown here, but I don't expect my students to draw that on a quiz or anything. Maybe in a homework when you have the ability to go back and look at your notes or anything. But there you go. So that's a way to make a primary amine. Now this is a primary amine, the first one. But what if we want to make a secondary amine? It's the exact same procedure, okay? So I can even copy and paste some of this. So if we actually, you know what? We could just copy this whole thing. Let's give it the old college try here. So if we just copy all of this, okay, and we'll put it down here. I'm going to run out of space, aren't I? All right, anyhow, you get the idea. So instead of this being our alkyl halide, we are going to have our, there we go, and we'll put iodide in there, and so that's going to give us this compound. We have our phenyl and our phenyl, and then to get to the final product, all we have to do is treat it with hydrazine the way we did in the first one, or you could do the two-step method. Let's give it a shot. Step 1 is H3O plus, and step 2 is going to be sodium hydroxide. They both work, okay? So what have we covered? Azide synthesis is a way to make primary amines, and also the Gabriel synthesis is a way to make primary amines. So let's write that down. We'll put here Gabriel Gabriel slash azide. Okay, those are ways to make primary amines. And we're actually going to look at another way to make a primary amine right now, but there's a reason why we saved this one for last. And this is reductive amination. It's a very, very useful reaction, very easy to set up. I mean, you guys have done enough work in the lab by now that you know that some things in organic chemistry are easy and some things in organic chemistry can be very difficult in terms of being in the lab. And all organic chemists, all chemists like reactions that are easy, you know, that aren't that challenging. It's nice to be challenged sometimes, but it's also nice to have reactions you can depend on. And reductive amination is a popular reaction. Why? Because it's very dependable. So check it out. What it does is it takes a ketone or an aldehyde, converts it to an imine, but then reduces it to the corresponding amine. Okay, so you guys know what a ketone is. Obviously, you know what an aldehyde is. You know what an imine is, or a Schiff base, as they used to be called. And we can take an imine and we can reduce that down to an amine. So it says the reducing agent, if a reducing agent is present, then the imine can be reduced in situ. So this should be italicized actually, but this is Latin for in place. Okay, the way it's shown here, it's like step 1 and step 2, right? You isolate the Schiff base or the amine, and then you do a hydrogenation with it. But there's a better way of doing it where you can do everything in one reaction, and let me show you. So instead of using a strong reducing agent like hydrogen or sodium borohydride or something like that, what we do is we use a milder reducing agent called sodium cyanoborohydride. It's a bit of a mouthful, but all you have to do is take sodium borohydride and just replace one of the hydrogen atoms on the boron with a cyano group, right? So you replace it with a CN group, okay, cyano. So remember that that's an electron withdrawing group. Okay, so that pulls electron density away from the boron. And what it does is it stabilizes the negative charge. And it means that sodium cyanoborohydride is not strong enough to reduce an aldehyde or a ketone, but it will reduce the imine once it's formed. So what's going to happen is in the first part, you're going to form the imine with your catalytic amount of acid in your amine. So let's say you started it with acetone and you treat it with ammonia, a catalytic amount of acid, and sodium cyanoborohydride. Again, we use NaBH3CN for sodium cyanoborohydride. Anyhow, I digress. What you would end up with in this case would be this imine. Okay, that's the intermediate after the first step, but then the sodium cyanoborohydride is going to reduce that down to a primary amine. So that's the treatment of a ketone or aldehyde with ammonia. If you use a primary amine, then you get a secondary amine. If you use a secondary amine as your nucleophile, you end up with a tertiary amine. And so now we have not only the azide synthesis and the Gabriel synthesis, now we also have reductive amination, which is a way to make primary amines. So now we have 3 different ways of making primary amines. And you can see that reductive amination, again, it's all in one pot. Okay, that's what we say. You're like, well, couldn't you just call it one reaction flask? Yes, because it's just a terminology or a vernacular, I guess, that organic chemists use. This is in situ. It's all done in the same flask, or in place is what in situ means. It's just Latin for in place. So you do it all together. So, come on, every chemist loves a reaction where you can just throw everything in a flask and mix it up, and walla walla bing bang, you get your final product just like that. So it says here, show 2 different ways of preparing each of the following compounds via a reductive amination. We don't have time to do all of these or the space to do all of these, but let's just solve the first one. And then we'll come back and look at another one, okay? But you see from the first one, you have, what would this be? Methyl dipropylamine is what you would call this compound. Methyl dipropylamine, or you could call it N-methyl N-propyl 1-propanamine. That would also be acceptable too. Either way is fine, okay? So there's 2 possibilities here. We could either put the methyl group on, or we could put a propyl group on our compound via a reductive amination. So let's say you wanted to put that methyl group on. The way you would do that is like this. You would start it with this secondary amine, okay? And then what you would do is you would treat that with the desired ketone or aldehyde. Now, in this case, you're only going to need a one carbonyl compound, and so it's going to be formaldehyde. So let me just move this out of the way. Okay, so I'll move this over here, and we'll say, okay, we're going to start with formaldehyde, right? That's going to be the source of our methyl group. Then what we're going to do is we're going to treat it with the amine, okay? Treat it with the amine, and our reagents are going to be a catalytic amount of acid and sodium cyanoborohydride, and that is going to add the carbonyl at this position, and so that's going to give us the product that we're looking for. Come on, iPad, 1, 2, 3. There we go, 1, 2, 3, and there you have it. There we go. So that's one way of doing it. The other way would be to start with an aldehyde that comes from these three carbons. So it would be starting with propionaldehyde, which is this compound. Move that over a bit here. And then we would treat it with what amine? Well, you'd have to have an amine with a methyl group on it and a propyl group on it. So, come on. There we go. Oops. What am I doing? All right. So let's see if we can come up with that amine. Come on, iPad. You're really not participating. Okay, there we go. So we have this secondary amine. So 1, 2, 3, like that. And then we're going to treat it with a catalytic amount of acid and sodium cyanoborohydride. And that is also going to give us the desired product. Like that. Give me a thumbs up if that makes some sense, those two disconnections, those two different ways of making this same compound. Okay? Let's just try one more quickly. You see that for C, there's two different disconnections you could do. You could either disconnect here or you could disconnect here, and you see that you end up with a linear compound. I'll just do one of them. Let's say you did the red disconnection. If you did the red disconnection, you would end up with, what would it look like? It would look like this. You'd have the carbonyl like this, and then you have 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And then you'd have the nitrogen over here, right? So what's going to happen is, right, it's going to attack at this position. So you're going to end up with that 6-membered ring. And so then you would just say, okay, everything is all put in here together. So I just need a catalytic amount of acid and my sodium cyanoborohydride, and that is going to give me the product like that. All right, there you go. So a little bit about reductive amination. Kind of running out of space on this one, but this is one that sometimes we make jokes about or whatever. But this is the synthesis of methamphetamine. So it says here, methamphetamine is used in some formulations for the treatment of ADD and can be prepared by a reductive amination of phenylacetone and methylamine. Draw the structure of methamphetamine. So phenylacetone, you guys all know what acetone is by now. So acetone is this. It's propanone. So if this is acetone, phenylacetone is just this. You take acetone and you put a phenyl group on it, okay? And then it says it's the reductive amination between phenylacetone and methylamine. Well, you know what methylamine is now. It's just CH3NH2. So if you do a reductive amination between those two, you should end up with methamphetamine. So let's give it the old college try here. No time like the present to make some meth. So if we take our phenylacetone and we treat this with methylamine, we need an acid catalyst, and we also need our sodium cyanoborohydride. And what's the compound going to look like? Well, let's see. It's going to look like this. So we're going to have all this skeleton, but now instead of a double bond, it's going to be a single bond, and it's going to be going to the nitrogen, which has a methyl group attached to it. So there you go. We end up with methamphetamine. All right. So if you put a hydroxyl at this position here, that gives you ephedrine or a pseudoephedrine anyhow. And, there's a way that, people take Sudafed and they convert it into meth. But anyhow, I won't get into all that kind of stuff there. But there you go. There's the synthesis of methamphetamine. Now, of course, there's a chiral center in here, and I'm not going to get into all the detail here. But this is the structure of methamphetamine. All right. Now that we've got that done, let's talk a little bit about synthesis strategy. I see somebody giggling. Okay. All right. One of my former colleagues once said, you know, the most exciting day in organic chemistry is the day we teach the methamphetamine synthesis. It's just like when you're in Boy Scouts, the most exciting day was the day you learn how to tie the hangman's noose or something. Anyhow, all right, so overall, we've come up with 3 different ways to make a primary amine. So we actually started out with this one. This is where we started, was sodium azide, and that does an SN2. And then I said you could reduce that using hydrogenation, or I'm going to scribble it in here if I can squeeze it in, or step 1 LAH, step 2 H2O. But that's a great way to make a primary amine. Also potassium phthalimide, and of course you get the potassium phthalimide from phthalimide itself. So, and you have to know, come on, there we go. If you take phthalimide like this, my friends, and you just treat it with potassium hydroxide, you're going to end up with potassium phthalimide. That can do an SN2. And then you can treat it with hydrazine to give you a primary amine. And then for the second step, I could put here, or step 1 is H3O plus, step 2 is NaOH. So that will work. And then the last way we learn is reductive amination. And reductive amination with ammonia gives you a primary amine. All right, give me a thumbs up if you're with me on all these. So all we're talking about is making a primary amine, one type of amine. Okay, there's a lot of different ways, and I don't remember exactly how he puts it in the book, but every once in a while he'll mention things like, why do you have to learn 3 ways to do the same thing? Well, you know, it's going to depend on your substrates, right? You're going to try all 3 of these probably, and whichever one gives you the best results, that's the one you're going to use, right? So that's why they call it research, right? You have to do it over and over to try to get the best result you can. So if you have a primary amine, like I told you when we talked about the exhaustive alkylation, right? That's kind of this thing here. This is the exhaustive alkylation, where your primary amine gets alkylated, then it gets more nucleophilic, secondary amine gets alkylated, tertiary amine gets alkylated, all the way until you get to a quaternary ammonium salt. And I told you last class that sometimes we call these quats. Okay, sometimes quats are found in cleaning products like those sanitary wipes, like Lysol wipes, or things like mouthwash, like Scope or Listerine or something like that. Quaternary ammonium salts can be found there. Anyhow, I like questions like this where it tells you what your starting material should be. So it says, using ammonia as your source of nitrogen. So this is all you have, right? It's just like a Survivor show or something. All you have is some ammonia as your only source of nitrogen. Show how you could make each of the following amines. Well, the first one is a secondary amine, and so we're going to have to use reductive amination for that. The second one is a primary amine. The third one's a tertiary amine. So there's a variety of ways you could do these, okay? There's not just one set path that you could use for these. But let's start out with this one here. And let's say if you wanted to solve this one and do a reductive amination, what you would need would be this carbonyl compound, so this aldehyde, right? And then it could react with the amine. So if we pencil the amine like this, right? And if you lose H2O from here, you would end up with the amine. Anyhow, so let's write that down. So we're going to start with our aldehyde, which is going to be this aldehyde. This is called acetaldehyde. Then we're going to treat it with ammonia. And, oh, did I say, it says ammonia is your only source of nitrogen. Sorry, I misspoke. So let's think here. We're going to have to do that. And we're also going to have to make, sorry, I was getting ahead of myself. We're also going to have to make this compound too. There's 2 compounds to make here. And so to make that compound, we're going to need an aldehyde as well. So let's draw the aldehyde that you would need there. So we'll start with this. So we have 1, 2, and then we'll put, there we go. So that's going to be our starting aldehyde. We're going to treat that with ammonia, a catalytic amount of acid, and sodium cyanoborohydride. That's going to give us the primary amine, which looks like this. And then to add that that ethyl group on, we're going to use acetaldehyde and a catalytic amount of acid. And then I'll write the sodium cyanoborohydride over here because my real estate is valuable here. So that's going to give us the desired product, right? We end up with this guy. And there we go. So we end up making this secondary amine. Let's try one more. If you wanted to make the second one, I think that one's a little more straightforward because it's a primary amine. So your starting compound in that case is going to be cyclohexanone. Or sorry, cyclopentanone. It's the only possibility. So you'd start with cyclopentanone, treat it with ammonia, then a catalytic amount of acid, and sodium cyanoborohydride, which looks a little something like that. And that's going to give you the product. All right, there we go. And the third one is in the exact same vein. All right, so those are some synthesis strategies. Everybody with me so far on making primary amines and then using reductive amination to make a secondary or a tertiary amine from a primary amine. All right, cool. So we haven't been talking that long, so I'm going to keep moving forward and get into section 22.8, which deals with acylation of amines. You can see that last class on Monday, I wrote this down. I said, this is actually a bit of review because we talked about this reaction in depth in chapter 20, right? The acylation of an amine using an acid chloride, right? We said, we kind of flipped it the other way around. We said you could take an acid chloride, treat it with an amine, and you end up with an amide like that. And if you remember, we said that we needed 2 equivalents of the amine, right? Because that cleans up the HCl and then it converts it into RNH3 plus Cl minus, right? You end up with a salt. Anyhow, so 2 moles of the amine and then 1 mole of the acid chloride. So if you're wondering, well, why is this showing up in this chapter? Because we already covered this in depth in chapter 20. You're right, we did. But now what we're going to do, before we just saw how acylation was used in things like aspirin synthesis, but now we're going to see how an acyl group can actually be a protecting group. So now we're going to get back to a protecting group. What was the protecting groups, or what were some of them that we've seen before? I'd say TMS, right? Acyl ether is a protecting group that we used during Grignard synthesis when we had an alcohol that we wanted to protect, for example. So why would you want to protect an amine? Well, take a look at this specific example here. If you remember back from chapter 18, an amino group is actually a strong activator. Strong activator. And so if you don't need to have any catalyst, no iron required. If you take aniline, so this is aniline, okay, I know you all know the name of the compound, aminobenzene or aniline. If you treat that with bromine, I mean, again, no catalyst required. It just brominates the heck out of it. It does polybromination. So you end up with this 2,4,6 tribromoaniline is what you get. And you get none of this compound, right? Now, the amino group is an ortho-para-director, but if you were thinking, oh, I just want to make this compound, I just want it to go in one place, it's not going to happen, okay? It doesn't work. And the reason why is because the amino group is too powerful of an activator, right? I said it's a very strong activator. So if we could mitigate or lower the activity of that amino group, then we could maybe do a monobromination. And that's exactly why we do an acylation, right? Because we go from a strong activator to a moderate activator, right? Remember that an amide is a moderate activator. So I'm going to put here strong activator for the amino group, but then when you do the acetylation, you end up with an amide, and this is a moderate activator. And so now if you try the bromination, you only get monobromination, one position, only in the para position, right? Because this is an ortho-para-director. So based off of sterics, it goes into the para position. And then it says here, the disadvantage of this synthesis is that hydrolyzing the amide, meaning breaking this bond here, so that's the amide hydrolysis, does require harsh conditions. So there's 2 possibilities. One is to just treat it with sodium hydroxide and you blow it apart, or the other one is actually a 2-step method. The first step is aqueous acid followed by sodium hydroxide, right? Because you'd end up with the anilinium ion. If you did this after step 1, you would actually end up with this, okay, NH3 plus, okay? And so you'd have to treat it with sodium hydroxide after to make the free base. But also if you wanted to do an alkylation on aniline, and this is something that we talked about a little bit in the electrophilic aromatic substitution section of chapter 18, we said that you can't do Friedel-Crafts on aniline, and the reason why is Friedel-Crafts requires a Lewis acid, like aluminum chloride. Well, as soon as the Lewis acid sees the lone pair, right, the lone pair attack, and now you've got a positive charge on your nitrogen. Now the ring is completely deactivated. So the take-home message is that aniline, you could say here, aromatic amines. It says here cannot undergo Friedel-Crafts directly. You could say not compatible with Friedel-Crafts. Okay, so what can we do? Well, of course we can acetylate it, right? If you acetylate it, you go from a strong pen. You go from a strong activator, right, to a moderate activator. Anyhow, and what that does is it renders this lone pair, right? This lone pair is very basic, very nucleophilic. Now the lone pair is delocalized up into here, and so it is not nucleophilic whatsoever. So when it sees the aluminum trichloride, meaning the Lewis acid, it doesn't form a bond with it, and so it works perfectly well to do a Friedel-Crafts alkylation on this N-acyl pyridine. So again, once you've done your alkylation, you got two options. You could either hit it with sodium hydroxide, that will give you the ephramine, or you could do the two-step procedure. Step one, aqueous acid. Step two, a little bit of base to neutralize that. All right, so now we've covered why you would do the acylation of amine. So if you're not sure, you don't follow me as to why or what is section 22.8 about, let me go back with you. Okay, let's review it quickly before we tackle a problem. Okay, so we finished reductive amination, and then we said, okay, we know what acylation of an amine is. Okay, it was covered in chapter 20 in detail. And the reason it's coming back up in this chapter is because an acyl group is actually a very good protecting group. So why would you need to protect an amine? It actually gives you two reasons, okay? So we'll put here a protecting group, and we'll put two reasons or two scenarios, you could say, are coming up. The first one, reason number one, is if you try to do a monobromination of aniline, doesn't work. So you end up with polybromination. And so what you do is you do an acylation, and then you get monobromination. The second reason why you would do it is because aniline and other aromatic amines are no good for Friedel-Crafts reactions. Why? Because they bind to the Lewis acid, which inactivates the ring. And so what you do is you acylate it, and then that allows you to install alkyl groups like a methyl or an ethyl or an isopropyl, et cetera, et cetera. So we got two reasons why we study acylation of amines. So let's take a look at question 22.20 and see if we can make some sense as to why we look at this in detail. This question I consider a really good one, and this one too. These are both good. So this 22.20 and 22.21. I know we have the answers in the solutions manual to these, but they're great questions. Slide 53. Let's see here. Aromatic ring in blue. So all I'm saying is that after step one, after this step, when you treat it with aqueous acid, it hydrolyzes the amide, but it would also protonate the amine, right? Because an amine is a base. So that's why you have to treat it with sodium hydroxide after. Does that make sense?
Yes, thank you.
Yeah, nothing to it. It's why it's Erica, it looks ridiculous, doesn't it? If you show this to somebody on the street, they'd be like, okay, this works. Then you got to do this first, and then the same thing a second time. It's a little ridiculous. But keep in mind the first one, this would be actually very strongly basic conditions, right? And this would be strongly acidic conditions. But then you just put it in weak sodium hydroxide to do the deprotonation. It looks kind of funny, but that it totally works. So with that in mind, it says when aniline is treated with a mixture of nitric acid and sulfuric acid. So I'm going to kind of sketch this out. If we take aniline, okay, and we treat it with a mixture of nitric acid and sulfuric acid, so HNO3 and H2SO4. It says the expected product would be para-nitroaniline. So we'll put para-nitroaniline. I'll write it the same way I did before. So para-nitroaniline. It says this is actually obtained in a very poor yield. Instead, the major product is meta-nitroaniline. Well, the reason this reaction doesn't work very well is because what happens in reality is not this, it's that we end up protonating the amine. So we go from an ortho para director, right? Once you have this, this is a meta director. And so after you do the nitration, what you're going to do is you're going to end up with this, where you have the nitro group in the meta position. All right, so that's why that happens. So let me just erase this, I guess. Anyhow, so that's what happens. So it says, rather than the orthopara director, propose a plausible method for converting aniline into paranitroaniline. So the question is, how can we take aniline? How can we take aniline and make this compound? If we want to make para-nitroaniline, well, the answer in that case is going to be if we install an acyl group, right? If we install an acyl group, we still have an ortho-para director, and so we can install our nitro group, and then we can just hydrolyze it in the end. So that's what we're going to do. So let's just practice this. I'll use my red pen here. So we're going to take aniline, and we're going to do an acylation. So we'll take aniline, and we're going to do an acylation. So if you want to, you could put, I don't know, you could put 2 equivalents of this or something. You don't have to. But anyhow, in that case, we're going to get N-acyl aniline. So that's this compound. And now we went from a strong activator, which can be protonated to form a strong deactivator. Now we go to a moderate activator where the lone pair on the nitrogen is not basic. And so now we can do our nitration using nitric acid and sulfuric acid. And that's going to give you the para-nitro compound. Comme ça, as we say in French. And then all we have to do is deprotect it. So we could do just sodium hydroxide. That will work. So let's just use sodium hydroxide, and that will give me the para-nitroaniline. Is that beautiful or what? So we end up with this and this. There we go. Does everybody follow me on the rationale for the acylation here? All right, cool. There you go. So that's all they're asking for in that one. The next one, it says starting with nitrobenzene. So if I read out nitrobenzene, and what else does it say? And any other reagents of your choice, outline a synthesis of parachloroaniline. So that's this compound here. Well, a nitro group is an ortho-para director, or sorry, a meta director. So that's not going to work. And if we reduce it, then we're going to end up with something that's going to be an ortho-para director. But let's just do that, and then we can discuss it further. So how do we reduce the nitro to an amine? Well, we learned a couple of different ways to do it. I'm going to use HCl and zinc together. And then in the second step, I'll treat that with sodium hydroxide. And that's just to free base the compound. And that's going to give me aniline. Oops. Yep. Sorry. There we go. And then once we have the aniline, remember that we can't just treat this with chlorine, because if we treat this with just Cl2, we're going to end up with this compound where we have a chlorine here, here, and here, and we have our NH2 group like that. So that's not going to work. And so let me just put that in a different color, because that's not what we're looking for. What we want to do is we are going to do an acylation. So let's see here. So we're going to treat it with acetyl chloride like that. And that is going to give us our N-acyl compound. And now we're set up to do our chlorination. So you can just put Cl2. That's what it does over here. If you look at, where is it? Where was it? It was back here, right? They just put Br2. So you could just put Cl2. If you want to put in the Lewis acid, you can, the catalyst. You can put in some iron 3 chloride or something if you want to. It's not necessary, but I'm just going to put here Cl2, and that is going to give me the parachloro compound. So we end up with something like this. And then to hydrolyze that, you got a couple of options. I'll just choose sodium hydroxide because it's easy. Okay, and there you have it. So there's the synthesis of parachloroaniline. A couple things to remember here is that this is a meta-director. This is an ortho-para-director, but it's too strongly activating, so you end up with, this trichloro compound. So you mitigate the reactivity by putting in the acyl group, and it's still an ortho-para-director, but you only get one chlorine installed instead of a holy host. Okay, so you would say here, I'd say this ring is too strongly activated. That's how I would describe that ring. All righty. So that brings us to the section on Hofmann elimination. It's named after David Hasselhoffman. I'm kidding. Anyhow, you might remember the Zaitsev product and the Hofmann product. So just to review, like let's say you had something like, I don't know, this, right? And then you treat that with a base like, sodium ethoxide. Well, you're going to get some SN2, but you're also going to get the Hofmann product, and you're also going to get the Zaitsev product. There's actually two of them in this case, but you end up with all of these compounds plus the SN2 product. And so you would remember this one, the less substituted one is the the more substituted one, Mr. Dion. These are Zaitsev, and the less substituted one is the Hofmann product.